this to the cloud. All right. Just so you guys know, you're being recorded. Although I'm sure the only thing that people can hear is me on the microphone on my headphones anyway, so you're fine, you're safe. Okay, so getting rid of that. Now, moving forward, we've skipped section 5.1. We're moving to section 5.2. 5.2, types of reactions. I'm going to try to be as quick and as vague as possible. Absolutely. Combination. Oh, thank you. So, combination reactions. Think about them as combining things. As you can see in the study guide, it's literally X plus Y becoming XY, formation of a covalent substance, or actually not covalent. In this case, it's an ionic substance. The example there is calcium, typically we would say solid, plus sulfur. This would probably also be, yeah, it'd probably be solid. In this case, since it's just Ca and S like that, giving you calcium sulfide, solid. Now, here's the next question for you guys. Did I post a video that actually went through the 4 phases that you're supposed to put at the bottom of the reactions? Okay. Let's just go through that extremely briefly. Okay. Oh my god. I got up to like 5.7 but didn't hit 5.7. Darn it. Okay, I need to fix that. Thank you for letting me know. Okay, so phases. There are the 3 traditional ones from chapter 1 plus aqueous. Okay, so you indicate this by, you have the symbol of the compound, and then in parentheses as a subscript, you put the phase. That's the general idea. Subscript, lower right-hand corner, in parentheses, indicates the phase. Okay, you've got solid, liquid, or an L, in however you want to do it, and gas. And then you've got, like I said, AQ, meaning aqueous. And the only reason I want to focus on that one is because it's the only one we haven't talked about. Okay, aqueous means you're talking about something that is soluble, that is therefore dissolved homogeneously or homogeneously, however you want to pronounce it, because they are both correct. One of those rare words that actually has multiple pronunciations that are acceptable. Homogeneously or homogeneously in water, hence aqueous, aqua, coming from the Latin root for water. Okay. Any questions about that? Good so far? Most of the time when we're talking about that, exceptionally most of the time, we're talking about ions. We're not talking about neutral things. We're normally talking about ions. There are very rare exceptions to that where you can talk about something that is not ionic, but most of the things that dissolve homogeneously into water are ionic. Okay. I shouldn't say exceptionally rare. There are small polar molecules like sugar that dissolve into water as well. Those are not ionic, but it's small covalent molecules or ionic stuff. And when we're talking about precipitation, it's ionic stuff. It's not iron, it's ionic. There we go. Okay. Any questions about phases? You guys understand how to indicate them, how to use them in general? Any concern? Okay. So that's that. Now, back to types of equations. Combination, you can see, is also known as synthesis, because how do you synthesize something? You combine things together to perform synthesis. Okay. A synthesis is from taking a bunch of stuff, smaller stuff, and building them into a larger single thing. Okay. You synthesize an idea from smaller, less complex ideas, so on and so forth. Questions about that? We got an example of that. Decomposition is basically the opposite of synthesis. Okay. Combination, synthesis, that's building larger things from smaller things. Okay. Decomp is exactly what you guys are probably thinking of if you are me or you have experiences in life that are anywhere similar to mine. You're thinking about things rotting, breaking down, so on and so forth. Decomposition is what we think about when we're thinking about things like fertilizers and all that. You think about that idea. Well, the same sort of thing is actually occurring in your fertilizer in decomposition. Literally, the chemistry of decomposition are decomposition reactions. You are breaking larger units into smaller pieces. And you can do that, for example, taking 2 copper oxide solid. You can break that off into copper solid plus 2 copper solids and oxygen gas, like so. That's it. That's the basic idea. Decomposition like that. Okay. And yes, that does happen. That does happen. Then we have displacement reactions. And really, the most useful term on there is single displacement or single replacement. And the reason I say that is the whole idea of single is important because you're starting with something, for example, like you could have iron solid plus, here we've got copper 2 sulfate that is aqueous, which means it's actually, what this is actually in solution is copper 2 plus that is aqueous plus sulfate anion that is aqueous. They are sitting there in the water surrounding the iron in that fashion. Question? Yes. Individual oxygen atoms do not naturally occur in nature. They just aren't stable. It's a diatomic. Let's see. Have I mentioned to you guys the 7 diatomics? Okay. There are 7 elemental diatomics that in nature occur as gases, and they literally on the periodic table, 6 of them form a 7 pointing at the 7th. That's the way I like to get people to see them. There are 6 of them that form a 7 pointing at the 7th. They are, to begin with, what are they? They are nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And yes, some people make a weird word out of that or a sentence out of that. I'm just going to show you how I remember it. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. There's a 7. And since there's 7 of them, oh wait, but that's only 6. The 7th one's right there. It's hydrogen. Naflubrihel. Pardon? Okay, perfect. Whatever you use to remember that, that is something that is there. And I mean, O2 gas is what you're used to breathing. Oxygen atoms are actually dangerous on their own. They're so reactive and so do not want to be on their own that you don't want them floating around like that. They are free oxides that will actually cause oxidative damage. And the whole idea of antioxidants is a real thing. Yes, the antioxidant supplement market is typically a snake oil salesman, which is ironic considering that real snake oil is actually useful as for like your muscles and things like that. But anyways, long story. Interesting history. Look it up sometime. It's fascinating. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Okay, plus hydrogen. Answer your question? Boom. Awesome. Okay. This also is actually an example of a precipitation reaction. Okay. Or no, this one is not. My apologies. This is not a precipitation reaction, but this does in many ways represent a potential net ionic equation. Because what you have here is these react and you get then what you get is you get iron iron 2 sulfate that becomes solid. No, sorry, aqueous. And then you add to it copper that is solid. And the exchange reaction that is happening here is the iron is entering solution and the copper is leaving solution. Now, there is actually a place where you would see sorts of reactions like this, and that is batteries. This is a potential electrochemical reaction. This will actually be potentially a type of redox reaction, potentially. And some substances that you can get to do reactions like this will absolutely be what you can use in a battery. Now, single displacement. It's called single displacement because the copper is partnered with the sulfur and the iron takes the place of the copper as far as partnership goes, and then copper is kicked out. Single displacement, so it displaces the copper. It's considered a single replacement because the copper is replaced. It's an exchange reaction because the iron exchanges positions with the copper. Okay. Moving forward, combustion. Combustion reactions have a very simple definition. This is, in general, the burning of stuff in O2 gas. So, what is fire? What are flames? Are they a substance? Can you touch fire? Is fire made of matter? Your simple response should be no. Now, I know traditionally, historically, people have gone, oh, there's 4 elements: earth, fire, wind, water, and of course the 5th one, heart. Go Captain Planet. Yes, not Captain America. Point being, fire is not an element. Fire is not a substance. Fire has no matter to it. What is fire? Fire is heat and light released very rapidly. And that is it. Released so rapidly that it causes a chain reaction. But it is only heat and light. There is a lot more to energy in general than we're talking about. We'll get there. We'll discuss that later. So what does this look like? Typically, you take some sort of carbon, and that's just a subscript for a number. Hydrogen. You could introduce oxygen. And technically, hell, you could even have nitrogen, sulfur, so on and so forth. The substances involved there vary. Carbon and hydrogen are the most common ones. So that's the ones I'm going to leave up there. We actually call these, so terribly surprisingly, the general name for a substance like this is a hydrocarbon. And I say that sarcastically because it describes exactly what it is. It's carbon with hydrogen. I love it when names make sense. Okay, it's a hydrocarbon. It literally tells you what it is. You can add to that oxygen gas, and what do you get? You get the oxides. Oxide products. Carbon dioxide. And, of course, H2O. Vapor, usually. Gas. Classic example of this, methane gas, CH4. I think I've said this before. Methane is odorless and invisible. You cannot see it, you cannot smell it. And you suffocate from it very quickly, of course, too. And of course, it's explosive, dangerous, etc. That rotten smell that you smell is hydrogen sulfide. It's added as an additive to the methane that you use in your house. And thank God for that, because then you can go, oh, I might be in danger. Okay, so you could use CH4. You could burn C6H12O6. Yeah, that's actually flammable. Anyone know what that is? If you don't remember C6, pardon? Tartrate? I don't think that's tartrate. In general, we consider this a hexose, usually, sugar. Most people, if you've sat through enough biology classes, you probably associate it with glucose being a hexose, but it's also the same chemical formula for actually 20 different hexoses. Glucose is just the most common one that people associate with it. Fructose has the exact same chemical formula like this. Add to those oxygen in either fashion, you'll get, again, CO2 and H2O, CO2 plus H2O. And obviously these are not balanced. You can tell by looking at them that there's no way these are balanced. Okay. Moving on, because that was combustion. Then we've got exchange reactions. I really prefer the name personally: double exchange, double replacement, double displacement, double the fun, double mint gum. Yeah, I have way too much stuff in my head. Jesus Christ. Way too much of my entity. I love the live transcription, by the way. It's going to be very fun for you guys to watch. It does a semi-decent job. Okay, so double exchange reactions, double replacement, double displacement. This involves generally two aqueous ionic or ionizable compounds or a gas. But the most classic example of these are things like there I have there silver nitrate plus sodium chloride. Anyone know what silver nitrate has historically been used in? Absolutely, that's one of them. You can also use it for photography, creation of mirrors, all sorts of things. Absolutely, you're absolutely right. In yeah, fuel as well. Absolutely. Silver nitrate plus sodium chloride. Both of these are aqueous and aqueous, and we can actually do a net ionic equation here. You look at your precipitation rules. Silver is insoluble in the presence of chloride, so you'll end up with silver chloride solid that precipitates. And you would only be able to predict this generally from your solubility rules. You'll have your solubility rules. Okay. So that means we have the formation of a precipitate. This is a precipitation reaction. That's a precipitate. A precipitation reaction means you produce a solid, an insoluble solid. More specifically, it's an insoluble solid, because there are solids certainly that will dissolve into solution. The whole point of it is that it precipitates as an insoluble solid called the precipitate. The name of that insoluble solid is the precipitate. So you end up with silver chloride, there's the solid there, and then sodium nitrate that is purely aqueous. We can do, we'll come back to your question, so I'm not going to show net ionic equation here right beyond that. Okay. That's the exchange reaction. Finally, here we have the neutralization reaction. Am I going too fast for anyone? Please let me know. So neutralization reaction, the most general description of this is when you take an acid and a base and you react them and you end up with water and some type of salt. Now, what is a salt? What is a salt? Very different from a salt. A salt is simply, in general, an ionic compound. Typically, salts are ionic compounds. A salt is an ionic compound. Of course, water is water. Acids are anything that is going to produce H plus in solution. Bases are typically anything that produces hydroxide in solution. And we will visit acids and bases in more detail in this class. Fascinating chemistry. That's the problem with chemistry, though. For someone who is fascinated by so many things, chemistry is a big candy shop because there are so many fascinating aspects of chemistry. Okay. Neutralization, you go from an acid and a base to water and a salt. Any questions? Okay, that's a definition. So classic example of this, hydrochloric acid, aqueous, added to, there's all sorts of bases out there, sure. Magnesium hydroxide. Simple enough. You add those together, you will end up with magnesium chloride that will be aqueous and water. That's an unbalanced equation. I have not balanced that. That is unbalanced. How do you balance it? Well, for this one, it's actually easy. You put a 2 there. Actually, it's not. I'm just kidding. If you look carefully, that's not actually completely balanced. I wanted that to be an easy question, but that's not the actual solution. You put a 2 there, it's still more complicated. Okay. Yeah, you put a 2 here and a 2 there. Now you're balanced. All right. Questions? Okay. So we've gone through 5.2. That is those different types of reactions. And essentially, I covered a little bit of 5.3. I already told you what a precipitation reaction is. I have told you you need to use the solubility rules. Let's see. Yeah, so whether a precipitation reaction will occur in mixed aqueous solution of 2 ionic compounds depends on the solubilities of the product. Okay, so 5.3 takeaways from that are, for a precipitation reaction to occur, one product must become an insoluble solid. That is one of the key things to that. Solubility is the amount of a compound that will dissolve in a given amount of a solvent. We go into that in greater detail in a different chapter. Concentration and things like that, molarity. With aqueous salts, if they combine to form a solid liquid gas product, that is called a reaction. That doesn't mean it's a precipitation reaction. If you produce a gas, that's not a precipitation reaction. Precipitation reaction specifically requires an insoluble solid called the precipitate, specific to precipitation reactions. There are other reactions that do occur. If all products are aqueous, soluble, with no new covalent bonds, because yes, there are exceptions to a lot of these things, with no new covalent bonds, this means then it is the situation known as no reaction. Okay. So if you throw a bunch of ionic stuff into solution and they remain ionic, there's no reaction. If you throw a bunch of covalent stuff into solution and they remain the same substances, there's nothing produced. You throw water in there with sodium chloride and it's still water with sodium chloride, there's no reaction. Not entirely true. There are some things there, but we're not going to go into that right now. By the definitions of this chapter, there's no reaction. Okay. You got your solubility rules at the top of page 5. How do you apply them? Well, you literally look at the things that you are putting in the solution and go, does it obey one of these rules for solubility? Sodium, lithium, potassium, cesium, and ammonium are always soluble. So if you see those in a substance, that means they are going to produce those ions. If you have sodium chloride, so on and so forth, any of those things, they break apart. If you add it to water, they break apart into sodium aqueous ions and chloride aqueous ions every time. If there's a sodium present and it's paired with something else, that anion will be soluble as well at that time. If there's nothing else in solution other than sodium, lithium, potassium, cesium, and ammonium paired with an anion, that anion will by nature be soluble because the cation is soluble. You need something paired with it to form an ionic compound in the first place. And if the cation is soluble, everything else is. Next, anions that are always soluble. Bicarbonate. So bicarbonate, nitrate, chlorate, and acetate are always soluble. Question. Oh, no, it's not. Oh, wow. Oh, my God. Okay, I'm retiring right now. No, it's not your bad. That's my bad. That was horrible. That is a sin. That's like 5 bonds to carbon or more than 1 bond to hydrogen. That is just as bad. Yeah, no, that's just as bad. I removed 2 electrons from chlorine. I made a positive ion of chlorine. I might as well lose my degrees now. It's over for me. Okay, a little over exaggerated, but that was bad. Thank you for pointing it out. Now this will be very funny to go back and listen to. Okay, so especially because no one will hear you, they'll just hear me talking. So it's just going to be me talking to myself. It'll sound like I'm talking to the voices of my head. It's going to be very amusing. Okay, so rule 3, chlorine, bromine, and iodine are soluble unless there is a lead 2, silver, or mercury 1 in solution. Okay, so what that looks like is if you had sodium chloride and it broke apart into sodium plus and chloride minus, and these were aqueous, and then a stray thing of suddenly later along comes a lead 2 plus that's aqueous, then what happens is these come together and form a precipitate of lead 2 chloride solid. And traditionally, this is how people would purify certain things from solution. And we still use this. I mean, honestly, chlorination of water, it does a lot of different things. It kills stuff. But one of the other things it does actually at times remove some toxic ions in this fashion. It's not perfect. It does a lot of other things too. But the point is, some of the things can be detoxified in this simple of a fashion. Same thing goes if you threw a silver ion in there or a mercury 1 ion in there. You would also see a similar reaction. Rule 4, sulfates are soluble except for those things when they become in contact with it. The following are insoluble unless with the following exceptions. Most of the following exceptions are Rule 1. That makes it nice and easy. It's all Rule 1 except for strontium, calcium, and barium paired with specific ions. You'll have these rules on the exam. I promise you that, unless they manage to print it badly again. I'll try to avoid that. I have a workaround. It's called me walking it into the print shop instead of emailing it to them. It should work nicely to be able to email things, but there's always a first. Good so far, guys? Solubility? Moving on. Okay. 5.4, acids, bases, neutralization reactions, blah, ionic compounds called salt. A neutralization reaction removes protons and hydroxide ions from solution and yields neutral H2O. The net ionic equation of a neutralization reaction is always, so the net ionic equation of when you have some sort of acid like this plus a metal paired with hydroxide is always going to be the metal paired with the anion A plus H2O. And the net ionic, this is usually aqueous, so the final net ionic equation will actually be H plus OH minus, giving you H2O. That's the final net ionic equation of that thing. It's the neutralization of protons and hydroxide, giving you liquid water. Okay, redox reactions. Still not enough time to go through this, but I needed to get to here if I also wanted to be able to go through any homework problems at all. Redox reactions are one of the heaviest concepts in this chapter. This chapter is heavy. Redox is one of the heaviest. So without further ado and wasting time, let's move on. 5.5. Redox. What does it stand for? Well, it actually stands for a combination of two reactions occurring together. Two what we call half reactions. And we call them half reactions because they can't occur without the other. They have to be paired together. They don't work in a vacuum. You cannot do these two half reactions separately and have nothing happen. They just don't. It doesn't work. So those two half reactions are oxidation, which is the loss of electrons, and the other half paired with this is a reduction reaction, which is, that's not a Z, that's an equal sign, a gain of electrons. Okay. Simple concept. And actually something we've actually looked at before. This goes back to when we talked about ion formation. Ion formation is a redox reaction. When you form a cation, that's an oxidation. When you form a reduction, that is, sorry, when you form an anion, that is a reduction reaction. Okay. Reduction reaction, gain of an electron. To form an anion, you have to add electrons onto an atom. That is therefore a reduction reaction. Production of a cation, you have to lose electrons. Loss of an electron, that's oxidation. So we've already seen this actually. You've been introduced to these reactions without knowing it. Okay. There are ways to remember this. Memory devices. I know, I can't remember. Mnemonic is spelled what? Something like MNEUMONIC. I think that's how you spell mnemonic. Something like that. Yeah, you get it. It's a memory device. Probably wrong, but who knows. Anyways, there's two of them. You have the lion, Leo Ger, which is loss of electrons is oxidation, gain of electrons is reduction. That's one of them. So if you like animals, Leo Ger is your go-to. If you are a big petrol head, fan of petroleum products, you love cars and big engines and burning long carbohydrate chains, then your other option is oil rig. Oxidation is loss. Reduction is gain. What they're talking about, of course, is electrons. Either one works. They're both tools you can use. You can feel dumb using them, but if you know what, if they are the difference between you getting an A and a B, if remembering these little things are the difference between getting an A and a B, or even failing the class and passing the class, who has the last laugh? The person who says, "Oh, you're dumb," and fails the class, or you for remembering these and doing better? You, clearly, because you succeeded where that other person got in their own way. Good so far? Okay, moving forward. So that is how we start to remember these things. This is all about electron transfer. Okay, so what we're looking at is the movement of electrons, the transfer of electrons. These cannot exist in a vacuum. That's why when I said, when we talked about this in chapter 2, you could not form a cation without forming an anion. You cannot do reduction without oxidation. Electrons have to come from somewhere. Electrons have to go somewhere. Okay. There always has to be a point of destination and a point of origin. So, blah, blah, blah. Moving on. Oxidation is loss, reduction is gain, reducing agent. Well, we'll get there. You know what? Actually, we'll do that right now because it's right there. So, a reducing agent causes reduction. If the most general term, agent, if you're a secret agent, you do something involving secrets. Okay. If you are a reducing agent, you cause reduction. If you cause reduction, that means the reducing agent becomes oxidized. So the thing that is oxidized is the reducing agent, is another way of saying that. The thing that is oxidized is the reducing agent. Okay, because if you cause reduction, you're causing something to gain electrons. If you're causing something to gain electrons, you yourself are losing electrons. Okay, makes sense, right? That's why I love this, is because if you can follow the logic, it's irrefutable. Okay, an oxidizing agent, by that same token, causes oxidation. Therefore, the oxidizing agent is reduced. If you're causing oxidation, you're actually taking the electrons. You're causing something to lose electrons, and the only way to cause something to lose electrons is to take them. Okay? If you are the agent of theft, you cause theft. Therefore, you take things. Okay? An oxidizing agent, therefore, becomes reduced. The oxidizing agent is the thing that becomes reduced. Okay? It's also very nice because these things are cyclical and redundant. Okay? And if you need to, you can also just do agent of reducing is the thing that is oxidized. And I don't want to keep doing that because I might get confusing. Let's not do that. That could get confusing. Reducing agent becomes reduced. Sorry, reducing agent causes reduction. The reducing agent causes, see how easy it is to get lost in the words as well. Okay. The reducing agent causes reduction. Therefore, the reducing agent becomes oxidized. That is the clearest way of saying it. Okay. Now, how do we tell if redox is occurring? And yes, I didn't explicitly spell it out, but you can see where the name comes from, reduction and oxidation. They got very clever. They went, let's take the two types of reactions and make a new word out of those types of reactions. Smart. Okay. So how do we tell if redox is occurring? We need a way to see electron movement, or a way to track electrons. Just like tracing money, if you want to see where the money is going, you need a way to count money. If you need a way to count money, you need a way to count electrons. And yes, I'm going to keep returning to the money analogy, okay, because it does work. Okay, so for the analogy, what we're actually going to track are charges, okay? And this works in both ways. So we are tracking electrons, which are negative charges. What sort of financial things are negative charges? I mean, that's a classic example, absolutely. Um, I thought I was clever when I said uh, credit card charges, but absolutely no, an overdraft fee is absolutely a negative charge. Absolutely, agreed. Anytime you do something that causes you to go into debt, taking on a loan, credit card charges are negative charges as well. Right? And no, I love your example. Yeah, absolutely. The most regular type of negative charge that you can do is the sort of thing that you do with like a credit card, right? Okay, so we need to track credit card charges, and they are negative. Okay, we're trying to track credit card charges, credit card exchanges. So for this purpose, we're going to use something called oxidation numbers. Okay, oxidation numbers, also sometimes called oxidation states, are imaginary values that are visualized by pretending all bonds are ionic and the more electronegative atom receives the electrons, which is actually what happens when you form a ionic bond. The more electronegative atom takes the electrons when you form a ionic bond. When you stick a fluorine next to a metal, the electrons from the metal transfer to the fluorine. Same with the chlorine. Sodium chloride, you end up with sodium cations and chlorine anions because the higher electronegative value of the halogen causes those electrons to transfer from the metal onto the halogen, be it fluorine, chlorine, iodine, or bromine. Okay. What that looks like is, very briefly, we saw this in chapter 1. Sodium solid, am I going too fast? I do apologize. Plus chlorine, and we'll just say a chlorine atom, even though it's not accurate. We'll just go with the chlorine like this. You put these two together in the same area, and you get a single electron that moves between them to give you sodium plus and chlorine ion. What that actually means is you've got the oxidation reaction that happens that is sodium solid becoming the sodium cation plus the electron, and you've got the reduction reaction that has to occur as soon as that electron is free and comes into contact with the chlorine atom to form the chloride ion. They happen at the same time, essentially, but they are two separate reactions as well. There's an oxidation reaction and a reduction reaction. These are half reactions, though, because they are only half of the story. The true story is the electron is moving from the sodium to the chlorine atom. Okay. Good so far? Okay. Back to oxidation numbers. Okay. It's an imaginary number, like I said. It exists because we're pretending that the world is only made of ionic bonds. It's not the true story, but we pretend. Okay. Now, as a tangent, yes, I am a bit of a stickler for certain things. Symbolism is important. It's how we communicate what things are. Symbolism, units, these things are important. It's how you communicate. So therefore, an oxidation number is sign followed by magnitude, the size of the value. Okay, that's why you see 2 plus as an oxidation number. If we're talking about a charge is a real thing. A charge is the actual value that exists on an ion. So therefore, we need to be able to tell the difference between an oxidation number and a charge. That is important. Real versus imaginary. Okay. I'm sorry, but unicorns don't exist. Horses do. So this is going to be magnitude followed by sign. And yes, there are people out there that have gotten lazy. There are scientists who just use one or the other of these to mean the same thing. That's lazy. That's unacceptable. It's going to continue. I know. I'm fighting a lost cause here, but I will do my best to fight on. Exactly. You're saying another thing. Yeah, just like if you left something without units. Same sort of conversation we had earlier. Exactly. If you put the sign first and the magnitude, that is an oxidation number. If you put that on an ion, you're technically saying that it's an oxidation number, not an ionic charge. And that's one of the things that my wife and I agreed on when we first met. We went, what do you think of oxidation numbers and charges? She said, it's sign and magnitude or magnitude and sign. And I went, here's a ring. No, my proposal was far worse and far more tragic. She deserves far better than something even that grand. Thankfully, I did better than Jace from Duck Dynasty, Jace Robertson. He just put the ring in a potted plant and said, "Here, honey, here's a potted plant. Why don't you dig around?" Brilliant. Yes, I've watched way too much Duck Dynasty. Bunch of idiots, but idiots with millions of dollars are fun to watch. People watch all sorts of idiots. So that's the general concept of the symbolism of oxidation numbers. Okay, but it is important. Now, how can you tell if a redox reaction is happening? When ions are involved, determine whether there's a change in charges. This is the bottom of page 6. Apparently the number didn't print, but it's at the bottom of page 6. For reactions involving metals and nonmetals, predict a gain or loss of electrons. Molecular substances can be analyzed in terms of loss or gain of oxygen, but that, again, is not the primary thing. That third one is just a byproduct. That's where the term originally comes from when it comes to oxidation, but it's not the full picture because there are a lot of things that do redox that have no oxygen involved. An atom is oxidized when it loses a share in electron. An atom is reduced when it gains a share in electrons. So how do we track these things? We need to be able to assign oxidation numbers. We need to be able to know how they change. So how to assign oxidation numbers. Okay, this is now about the top of page 7. First one is any atom in its elemental state, meaning pure elemental homogeneous elemental. The whole point I'm trying to make is it's one element by itself, but that doesn't mean one atom by itself. Okay, we're not talking one atom. We're talking about one element can be more than one atom of same element. So you could have iron solid, but you can also have oxygen gas. You can have P5 solid. I mean, you could have C 60 solid even. It doesn't matter. These are all elemental forms because they are just the element by itself. It doesn't matter the number of atoms. It matters the number of elements. Number of elements matters. If they're by themselves, there's no difference in electronegativity. There's no pretend ionic bond. No difference in electronegativity. No pretend ionic bond means the value here is 0. So you assign a oxidation number of 0 to any pure elemental substance. Oxygen gas, solid carbon, solid phosphorus, solid sulfur, solid metals. If they're pure metals, they have an oxidation number of 0. Okay? Good so far. Okay. Next. Monoatomic ions. The oxidation number has the same magnitude and sign. So magnesium 2+ means the oxidation number is +2. Sodium plus means the oxidation number is +1. Again, straightforward. Okay, very easy. Should not have to memorize that in general. It should just be almost instinctual. It makes sense. It's logical. Okay. By that same fashion, of course, Cl-, the oxidation number is -1. Nitride, N3- is -3. It all follows the same rule. Good so far. Okay. Next one. Then, you guys, am I going too fast? Were you all right? Okay. Next thing on there then are the following rules. Hydrogen, in general, unless paired with a metal, is equal to +1 if it's in a compound with other elements, especially with other nonmetals. Okay. Remember, H2 has a oxidation number of 0 because it's elemental. H2O is where you see +1. Okay. So H2 is 0. H2O, hydrogen is equal to +1. LiH, that's a metal. Lithium is a metal. So here, hydrogen is actually equal to -1. Most of the time, we won't look at what's called a hydride anyway, but I do like to let you see these things. Hopefully it doesn't confuse you. Moving on. Oxygen is equal to -2 in compounds, with a few exceptions. Yes, there are some exceptions. However, it's equal to -2 unless with fluorine, essentially. In that H2O, oxygen is equal to -2, so on and so forth. Almost always oxygen is -2. Almost always hydrogen is +1. By these same rules, nitrogen is typically -3 unless with something more electronegative than it. So if nitrogen is paired with oxygen, if nitrogen is paired with chlorine, potentially. If it's paired with fluorine, potentially. However, if nitrogen is paired with phosphorus, if nitrogen is paired with carbon, it will have -3. Okay. Halogens are typically equal to -1, but again, there are more exceptions. The most common ones are oxygen is equal to -2. To remember, oxygen is equal to -2, hydrogen is equal to +1 when they're not on their own. These are very straightforward ones. They're very rarely exceptions. Halogens are typically -1, but there are a lot more exceptions to this. You must look at the electronegativity. Okay. For compounds, the total sum of the oxidation numbers in it will be equal to 0. Now, rather than just babble on about that definition, I'll show you. In H2O, here we know hydrogen is equal to +1, oxygen is equal to -2, and by that, of course, there's 2 of the hydrogens, +1, plus 1 of the oxygens, which is -2, giving you a total of 0. You can also use this to figure out oxidation states. Okay. Example, if I don't know what an oxidation state is, but I've got something like carbon 6, hydrogen 12, oxygen 6, well, I can go, okay, oxygen is equal to 6 times -2, hydrogen is equal to, what is it? Oh, there's 12 of them times +1. Carbon is actually neutral. So you apply the rules that you know for sure, and then you worry about it later. You worry about the ones that you can't define easily, okay? That's why you also look at carbon with hydrogen here. Hydrogen is equal to +1. Carbon, therefore, is equal to, well, what you do is you go carbon plus 4 times +1 is equal to 0, which means carbon here is -4. Okay. Subtract 4 onto the other side, you end up with carbon is equal to -4. By that same idea, CO2 here, carbon plus 2 times -2, the oxygens, is equal to 0. Carbon is equal to +4. Any questions or concerns about this? It's okay if you're confused. Please let me know. Doing okay? I know it's a lot of information. Yes, it is. You got it. Questions, concerns? Moving forward? Okay. So that brings us to how do you track redox? Look for changes in oxidation numbers. Okay. So first, that basically ends the general gist of what I wanted to say there. Okay. Bloody hell, I'm running way out of time. Okay, so let's go to homework questions. I wanted to get to net equations. It's not going to happen. I tried on Tuesday. It didn't happen. No matter how fast I try to move, there's no way you can cover like 2 to 3 lectures in this short of a time. So, homework question is 45. 45 was complete the following precipitation reaction using balanced chemical equations. Let's see. Blah, blah, blah. So, iron sulfate and strontium hydroxide. Iron to sulfate, I think it's aqueous, plus strontium hydroxide. I'm okay doing this because the handout I gave you guys that's due next week is a whole bunch of these different types of reactions. Net ionic equations, redox equations, and then balance the equation plus, I handed that one out, right? Okay. See, I'm so doing so much. Blah, blah. Anyways, so how do we do this? Well, first you break this apart. If it's aqueous, you break it apart into its ionic components. You go, okay, I've got iron, I mean, you could balance the equation first, but let's just break it apart. Iron 2 plus strontium, that's not strontium, sulfate aqueous plus strontium, which is going to form a 2 plus aqueous plus 2 hydroxides or aqueous. Okay, what are our products? You can see that, well, I need to look at my solubility rules here first. That was page 5. Well, let's see, blah, 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 blah. Sulfates are soluble unless strontium's there. Okay, sulfates are soluble unless with strontium. That's rule number 4. So this becomes strontium. You can see what happens here is this is a double exchange reaction, a double displacement reaction, a double exchange reaction. It's 2 aqueous substances that come into contact with each other, so they're going to swap partners. Okay, that means we're going to end up with strontium hydroxide to begin with. That's how I knew I needed to look at strontium hydroxide to begin with, is I looked at that and saw them swapping. Okay, the other thing that's happening here is we end up with iron 2 hydroxide. That's the other product. Okay, now you look through your rules. We know that the strontium hydroxide is a solid. Hydroxides are insoluble unless paired with something like that. We actually end up with 2 solids here. This is ironic. Oh, you're right. It has been a long day. Strontium sulfate. Yes. Thank you. Sulfates are soluble except when paired with strontium. So same result, but no, we don't end up with just pure hydroxides. Thank you. There we are. So there are our products. There are precipitation, our precipitate products. Now our final reaction becomes, of course, their FeSO4 aqueous plus SrOH2, like that, aqueous, giving us FeOH2 solid. This is unusual. I will tell you this. This is unusual. Generally, you don't form everything solid. There is no change in the net ionic equation here because there's no spectator out. No one is just sitting around. Everyone forms a part of the product. This is unusual, which is actually why I kind of like this question, because it is an interesting situation. Strontium sulfate, SO4 solid. There we go. So good so far. Okay. It's later than I wanted. Bloody hell. Wanted to get out of here early. Okay, you guys okay if we just stopped? Okay. It's way later than I wanted to begin with. Thank you for your time. Thank you for showing up. I want to make this worth your guys' time, so thank you.